12.1, you're going to learn about tangent line. A tangent line is in a plane of a circle that intersects a circle in exactly one point. The point P is the point of the tangent. Theorem 12.1 says if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. Theorem 12.2 says if a line in the plane of a circle is perpendicular to the radius at its endpoint on the circle, then the line is tangent to the circle. Theorem 12.3 says the two segments tangent to a circle from a point outside a circle are congruent. So which means that line AB and line CB are congruent. Problems for chapter 12.1. In this case, you have to use theorem 12.3. Since the two segments are tangent to the circle from one point outside a circle, and which is they're congruent, AD and AB are congruent, so that makes you 2 10 centimeters, and DF and DE are congruent, so this is 215, and BC and CE are congruent, so which means there's 2 feet. So which gives you 10 times 2 plus 15 times 2 plus 8 times 2, and it gives you 66 centimeters as the perimeter of the triangle ABC.
Chapter 12.2, Theorem 12 through 4 states that within a circle or in congruent circles, number 1, congruent central angles have congruent chords, and congruent chords have congruent arcs, right there. And number 3, congruent arcs have congruent central angles, right there. Theorem 12.5 states that chords equidistant from the center are congruent, and congruent chords are equidistant from the center. Theorem 12.6 states that in a circle, a diameter that is perpendicular to a chord bisects the chord and its arc, which makes these two and these two congruent. Theorem 12.7 states that a diameter that bisects a chord is going to be perpendicular to that chord. 12.8 states that the perpendicular bisector of a chord contains the center of the circle. These are the practice problems for chapter 12.2.
I'm doing 12.3 inscribed angles, and our first major concept is pretty much that this section AB, our arc AB, is called an intercepted arc, and angle C is called an inscribed angle because it's inscribed in the circle. Alright, now we see our first theorem come into play, and this is theorem 12.9, and it's the inscribed angle theorem, and it pretty much states that the measure of angle B is half of the measure of arc AC. So if we had arc AC being 100, since measure of angle B is half of that, it would be 50. Alright, now we're going to practice the inscribed angle theorem, and actually for this you have to do the steps in order. If you do them out of order, the equation really does not work. Okay, so first of all, we have to solve for A before solving for B. And in this situation, A is going to be 2 times of angle Q, which is 60, because we see that the measure of angle Q is going to equal half of the measure of PT in this case, and PT is A, and the measure of angle Q is 60, so A is going to be 120 degrees. So 120 degrees here for A, and now that we have A, we were able to solve for B. So for B, we're going to have to do the measure of angle B equals half of 120 plus 30, because in this case B is equal to P, or the angle B is covering the arc of P, T, and S. So PTS covers 120A and TS, which is 30. So it's going to be half of 150 equals the measure of angle B. Okay, so the half of 150 is 75, and that is what angle B is going to equal. So now that we've solved for both variables, we have A equaling 120 and B equaling 75 degrees. We're going to be talking about the corollaries to the inscribed angle theorem, and we see that the first corollary is two inscribed angles that intercept the same arc are congruent. So since angle 2 and angle 3 intercept the same arc, they're going to be congruent. So for instance, if angle 2 is, the measure of it is 45 degrees, it's going to be likewise with angle 3. The second corollary, and that is that an angle, angle 1, inscribed in a semicircle, is a right angle. It's kind of self-explanatory. Semicircle, and since it's inscribed in it, angle 1 is going to be right angle. Corollary 3 states that the opposite angles of a quadrilateral inscribed in a circle are supplementary. So if we have a quadrilateral, we know that the angle measurements in it are going to equal up to 360. And so it's stating that the opposite angles in the quadrilateral are going to be supplementary, which means that they're going to equal up to 180. So angle 1 and angle 2 are supplementary to each other. From 12.10, and it states that the measure of angle C equals half of the measure of arc BDC. So we have arc BDC here, and its measure of angle C is going to be half of that arc. I'm going to practice theorem 12.10, which is this right here. In this case, it's going to be the measure of angle W equals half the measure of BDC, which in this case is going to be 246, that arc right there. And when we put 246 divided by that, divided by 2, we're going to get the measure angle W equals 123. And that is the practice of theorem 12.10, which is that right there. These are the practice problems that I came up with for section 12.3, and these should cover the main theorems, and here's a word problem to go with it. And this concludes the review of section 12.3.
Secant is a line that intersects a circle at 2 points. When I erase this, it's still going to be a secant, which is going to be a ray AB. And then if I erase this, it's going to be segment AB. Theorem 12.11 says the measure of angle formed by two lines that intersects inside a circle is half the sum of the measures of the intersected arcs. But let's say this is angle, this is x, and this is y. And let's say this is angle 1. Half of x plus half of y is equal to 1. The first one is when both secant lines touching the circle and still intersecting outside the circle. And the second one is when one line being tangent to the circle and one just being a secant to the circle. And the last one is when both lines tangent to the circle and with intersecting outside the circle. The equation to find x and y is measure angle A equals 1/2 x minus 1/2 y. Theorem 12.12 says for a given point and circle, the product of the length of the segments from the point to the circle is constant along any line through the point and the circle. For this equation is a times b equals c times d. For this one, w plus x times w equals y plus z times y. For this one, y plus z times y equals t squared is the equation to find the missing letter. Practice problems for chapter 12.4.
Chapter 12.5. Theorem 12.13 says that an equation of a circle with the center hk and the radius r is x minus h squared plus y minus k squared equals r squared. And this equation is in standard form. So you use this equation to find the radius over there.
Chapter 12.6. A locus is a set of points, all of which meet a stated condition. To sketch a locus, draw points of the locus until you see a pattern. So, for example, you have point C, and you have a circle around it, and you have points that are all 1 centimeter away from each other. So the stated condition is they must all be 1 centimeter away from point C, and the pattern is they're all 1 centimeter away from point C again. Now we're going to do a practice problem. So draw and describe the locus. In space, the points that are C units from a point D. So first we have to draw the locus, and it's a circle around point D with a radius of C. The locus is a sphere with the center at point D and the radius of C. These are 3 practice problems for section 12.6. The first is to draw and describe the locus in plane, and its points 3 millimeters from a line LM. The second is give 2 examples of loci in everyday life, 1 in a plane and 1 in space. And the third is make a drawing of the locus, the path of a doorknob as a door opens.